Hey, welcome back. Today we're stepping into what is basically the world's biggest kitchen, the world of industrial chemistry. We're going to pull back the curtain and see how chemical engineers use these super precise recipes to create, well, pretty much everything that builds our modern world.
So let's just start with a massive question. How do you cook for 8 billion people? I mean, it sounds completely nuts, right? But it's a puzzle that chemical engineers are solving every single day. From the fertilizer that grows our food to the plastics in our pockets, it all begins with a chemical reaction that's been scaled up to a size that's almost impossible to imagine. You know, just like any great chef, you absolutely need a perfect recipe. And in our giant industrial kitchen, that recipe is the foundation for everything. It's got a very specific and, maybe a little intimidating sounding name.
And that name is stoichiometry. But don't let the word scare you. All it really is the ingredient list for your chemical reaction. It tells you the exact proportions of molecules you need to combine to get the product you want, ideally with nothing left over. It's precision cooking on a molecular level.
And this is exactly why getting the recipe right, or balancing it, is so crucial. Look at that top row, the unbalanced one. It's a total mess. The atom counts just don't add up. You start with 4 oxygen atoms and somehow end up with 3? No way, that can't happen. But the bottom version, the balanced one, that is our perfect recipe. You see how the atoms are perfectly equal on both sides? That's the law of conservation of mass, right there in action. You can't create or destroy matter.
Okay, but what happens when you don't have the exact amount of everything you need? In the real world, in these massive industrial kitchens, you almost never do. And this brings us to the very practical problem of leftover ingredients.
And here's the reality of it. You almost never use the perfect recipe amounts. Why? Well, it usually comes down to money. Let's say one of your ingredients is super expensive. You might just flood the reactor with a much cheaper ingredient to make absolutely sure that every last molecule of that pricey stuff gets used up. It's just smart economics.
So this sets up 2 key roles for our ingredients: the limiting reactant and the excess reactant. The limiting one is simple. It's the ingredient that's going to run out first. It's the bottleneck. It sets the absolute maximum amount of product you can possibly hope to make. And the excess reactants? Well, that's everything else you've got floating around after the limiting one is all used up.
So how do you figure out which is which? Well, engineers run a really quick calculation for each ingredient. So in that sulfur trioxide example we just saw, the sulfur dioxide, SO2, gets a score of 0.5. The oxygen gets a score of 1.0. The rule is dead simple. Whichever ingredient has the lowest score, that's your limiting reactant. That's the key that controls the whole process.
All right, so you've run your reaction, you've identified your key ingredient, but how do you know if it was any good? How do you grade your cooking? To figure that out, we need a way to measure success. And the first, most direct measure is something called fractional conversion. Really, it's just asking a simple question. Of the main ingredient I put in, what fraction of it actually got used up? It's a simple percentage that tells you how far your reaction went. But of course, things get a little more complicated. Sometimes your ingredients get creative. They decide to react in ways you didn't plan for. It's like you're trying to bake a cake, but you accidentally end up with a pile of burnt cookies on the side. We call these side reactions. And here's a perfect real-world example. When you're making ethylene, which is a crucial building block for all sorts of plastics, you only want that top reaction to happen. But as you can see, other reactions can pop up, creating things you don't want. And every single molecule that goes down one of those wrong paths is basically just lost profit.
So that brings us to 2 more really important metrics: yield and selectivity. Yield is pretty straightforward. How much of the good stuff did you actually make? But selectivity is more subtle. It asks, how good were you at making only the good stuff and not all those other unwanted side dishes? A process with high selectivity is elegant, efficient, and profitable.
Now, get ready for a really fascinating twist. What if your cooking process could just start uncooking itself? It sounds wild, but some reactions don't just go in one direction. They can actually run in reverse. This quote from our source material really says it all. For a lot of reactions, as you start making your products, those products can actually start reacting with each other to turn back into the ingredients you started with. This leads to a state called chemical equilibrium. So you've got the forward reaction, which turns your ingredients into products. But at the same time, you have the reverse reaction, turning those products back into ingredients. When you're at equilibrium, it doesn't mean everything is stopped. It just means those 2 reactions are happening at the exact same speed.
It's like a two-way street with perfectly balanced traffic flowing in both directions.
And this is the part that's so important to remember. Equilibrium is not a dead end. It is a state of perfect dynamic balance. From the outside, it might look like nothing is happening at all, but down at the molecular level, it's this constant, furious dance of molecules breaking apart and reforming over and over again.
So, how do all these ideas, these recipes, the leftovers, the reactions that run backwards, how do they all come together in the real world? Let's take a look at a process that literally changed the course of human history.
Let's walk through this quick case study on ammonia production, the process that makes modern fertilizer possible. Step 1, you feed in your ingredients, nitrogen and hydrogen. Step 2, you run that quick calculation and identify hydrogen as your limiting reactant. And step 3, knowing your conversion, let's say it's 10% for this run, you can calculate with incredible precision that you'll be making 40 moles of ammonia every single second. It's a perfect marriage of all these principles.
This chart is a great way to picture what that 10% conversion actually means. If we just look at our limiting reactant, the hydrogen, we can see that in one trip through the reactor, only 10% of it was actually used. So what about the other 90%? Well, in a real plant, that unreacted gas is captured, separated, and piped right back to the beginning to be used again. Nothing goes to waste.
And in the end, these seemingly abstract recipes and calculations have massive, world-shaping impacts. You've got ammonia synthesis for fertilizer, which feeds billions. You have ethylene production, which creates the world's most common plastic. And you even have reactions that are key to producing hydrogen for fuel and could one day be used to make oxygen for astronauts on Mars. It's amazing stuff.
And that brings us to one last thought to leave you with. We saw how chemical equilibrium can put a hard limit on how much product you can make. So what do you do as an engineer when the fundamental laws of chemistry tell you that no matter how hard you try, you can only ever convert, say, 67% of your main ingredient in one go? That is the kind of puzzle that drives real engineering innovation. Thanks for tuning in.